Okay, here we're going to consider tension and Newton's third law, and then how this can be applied to a tug of war. We've already seen that forces on opposite ends of a string are equal and opposite, but do they constitute an action-reaction pair? And the answer here is formally no, they're not an action-reaction pair. To consider that, let us actually look at what the action-reaction pairs are in this example. So let's take this example and blow it up a little bit. And we can see that we have one pair of action-reaction forces right over here. That's namely you pulling on the rope right here, and then the rope pulling back on you. That's an action-reaction pair. These two have to be equal. You pull on the rope pulls back on you. There's a second pair over here, which is the rope pulling on the block, and then the block pulling back on the rope. This over here is another action-reaction pair, and this has to be equal by Newton's third law. Notice Newton's third law does not connect the first pair to the second pair. To connect those two forces together, let's consider Newton's second law, which says the net force acting on the rope must equal the mass of the rope times the acceleration of the rope. The net force will be this force right here, F1, which is acting to the right, so we'll call that positive, minus F2 prime, which is acting to the left. That's our net force. That equals the mass of the rope times the acceleration of the rope. We will always assume that our ropes are extremely light or essentially massless. If that is true, then this product will be essentially zero, which means these two forces must be equal. So F1 right here will be essentially equal to F2 prime because there's no mass in between them. That also will mean that F2 over here will equal F1 prime over there, which is what we had over here. Namely, these two forces are equal and opposite because of Newton's third law plus our assumption that our ropes will be massless. Note we can also do this reasoning all along the length of the rope and say that the tension will be equal all throughout the length. So to say this is an action-reaction pair is a little bit of a simplification. They technically aren't. We'll treat them as such because we're going to assume that the rope right here is essentially massless. This then leads us to the assumptions we're going to make about strings, ropes, cords, and whatnot. We're always going to assume that they're essentially massless. Or what that really means is that their mass will be much, much smaller than anything else in the system. So therefore we can neglect their mass. We will also assume that they will not stretch, or their length is fixed. What that means is when they apply forces, the two objects they're attached to will always have the same distance in between them. And we will assume that the ropes will apply whatever force is needed to keep those two objects moving together and keep the length fixed. We may say they can do that, but up to a maximum force. And after you exceed that force, the string breaks and the two objects move separately. So we may provide a maximum tension force, and we'll assume that the string or the rope can apply whatever force it needs to up until that maximum value. We will also assume that they are completely flexible, perpendicular to their length, so they can only apply a force along their length. Tension forces will always be parallel to the rope. This means ropes are effectively only going to be a medium to transmit forces. They will not be objects in and of themselves. So we will not effectively draw free body diagrams for a rope because the mass of the rope will be zero, and the forces on either end therefore have to add up to zero. And we'll use that medium, this only as a medium to transmit forces between objects that are not otherwise in contact. So your hand can apply a force to a block without touching the block if we put a rope in between your hand and the block. So these are the assumptions we're always going to make about ropes. And they're actually pretty good because ropes usually are going to be much lighter than whatever it is we're going to attach them to. So this now brings us to the tug of war. How do you win a tug of war? Now, and again, note, what we're assuming is the rope right here that we're using is very light compared to the people involved, and that's probably the case. First, consider, can you pull harder on your end than your opponents do? And the answer is no, you can't. These two forces essentially constitute an action-reaction pair. Formally, they are not, but we'll treat the rope as massless, and effectively, they will be. So now, what are the unbalanced forces that do allow you to win a tug of war? Well, one of them is friction between the ground, so that you can grip the ground harder here than your opponents do, and in particular, you can pull on the rope harder than your opponents can grip the ground. If you can do that, then there'll be a net unbalanced force acting on your opponent, and they will move. Second thing you can do is grip the rope harder than your opponent is gripping the rope, and thereby move the rope. Because that, again, does not constitute an action-reaction pair. The friction on the ground and the friction on the rope are not action-reaction pairs. Those can be unbalanced. So those are the two ways you can win a tug of war. The next thing that people often ask is, well, doesn't it really help to have a very massive team? And the answer is formally, mass doesn't help you win. This really determines how rapidly you're going to move. And remember, inertia is not a force. And what you're looking for is applying unbalanced forces. To see how mass effectively doesn't really help you, consider the following example. We'll take a very massive team on one side, but we're going to put them on roller skates. We're going to put a much lighter team on the other side. They're going to be on the ground, and we're going to allow them to wear cleats. Note who's going to win. Obviously, the team on the roller skates, even though they're more massive, is not going to win. They have no traction on the ground. All the heavier team is going to do is, as they pull on the rope, they're just going to pull themselves closer to the other team. Their mass will determine how rapidly they will move in response to that force. The mass doesn't help them. Summary, what have we just discovered? That forces on opposite ends of a string or a rope are not formally action-reaction pairs. They will essentially be that because we're going to treat ropes as merely mediums to transmit forces. Regardless of the fact that there could be differences on either end of a rope, that's determined by the mass of the rope, and that's always going to be small. So that means you can't pull much harder on one end of a rope than your opponent can pull on the other end of a rope in a tug of war. Therefore, tug of wars are won by friction. Friction between your feet on the ground and your hands on the rope. They're not won by pulling harder on the rope.